Hello, I am Michele Scquizzato and I'm going to be talking about green paging and parallel paging. This work is about paging, the task of managing the memory system of a computing device. This is usually studied with this simple model. We have a fast memory, which can hold up to k pages, and a slow memory of unbounded capacity. We're given a sequence of page requests. In order to service a page request, that page has to be in fast memory. If it's not in fast memory, then we have a page fault. And that page has to be brought into fast memory from slow memory. In doing so, if the fast memory is full, the paging algorithm is also faced with the decision of choosing which page to evict in order to make room for the new page. The goal is to minimize the total number of faults. So paging is an intrinsically online problem in a sense that at the time when a request is issued, future requests are not known. This is studied through the analysis of the competitive ratio, which is the fraction between of the number of faults in an online algorithm and the number of faults in the offline optimum algorithm. This is a deeply understood problem. In this paper, we focus on two variants of this problem. In the first one, which is what we call grid paging, the paging algorithm can vary memory capacity between k and k over p. A page hit takes 1 unit of time, whereas a page fall takes s units of time, where s is much bigger than 1. And the goal is to minimize the integral of memory capacity over time, a quantity that we call memory impact. So this is a simple model for studying the total memory used by a computation. And it's motivated by low power computing or cloud computing. The other problem we study is parallel paging. Here we have P processors that share the same fast memory. So we have P sequences of requests with disjoint sets of pages. A page hit takes, again, 1 unit of time, and the page fall takes s units of time. The goal here is to minimize some function of the completion time of the sequences of requests. A clear motivation is multi-core processors. So this problem is a classic problem, has been investigated for a while, usually under simplified models. This model has been introduced around 10 years ago, but we don't know yet lower bounds, and we don't know competitive algorithms. So here is our results. So we have an equivalence result, which is as follows. Basically, it says that green paging is essentially equivalent to parallel paging, in a sense that any green paging algorithm can be translated into a parallel paging algorithm in a black box fashion. And this translation is also efficient. Then we also have that under some conditions, any parallel paging algorithm can be translated into a green paging algorithm in a black box fashion. Moreover, if a green paging algorithm has a competitive ratio of at least alpha, then any parallel paging algorithm has a competitive ratio of omega alpha for average completion time. And the other set of results is time bounds for green paging, because we can focus on just one of the two problems because of the equivalence result seen before. For green paging, we can show these two results. No deterministic online algorithm can be better than order log p competitive, not even with a constant factor of resource augmentation. And there is a simple deterministic online green paging algorithm which allocates memory in a totally predetermined way, and which is order log P competitive if provided with a constant factor of resource augmentation. So these results automatically give the following corollary, which says that the same bounds apply to parallel paging as well. So I conclude with what I believe are the two main takeaways of this work. The first one is that green paging is the right way to think about parallel paging. And the second one is that the price for not knowing the future in these two problems is order of log P. Thanks.